So this lesson is an introduction to Le Chatelier's principle, and we're going to be looking at Le Chatelier's principle in detail in a laboratory, but just as an introduction, what Le Chatelier's principle tells us is that if a system at equilibrium is disturbed by either a change in temperature, a change in pressure, or a change in concentration of one of the components, then the system will shift its equilibrium position so as to counteract the effect of the disturbance. Meaning, if a reaction is already at equilibrium, there are three different ways in which you can force the equilibrium to be shifted. That's either changing the temperature, changing the pressure, or changing the concentration of one of the constituents of that reaction. So the first change we're going to look at is actually concentration. Now, if you look here, this is a nice review. I'm going to give you it to you in chemistry terms, and then I'm going to give you a real-world example to make it make more sense. So for concentration, if you add a substance to a system that's at equilibrium, then the system is going to react in order to consume some of that substance in order to reestablish equilibrium. So if you notice here, you've got a pink and a blue substance. If you add more of that blue reactant, what that's going to do is it's going to cause a shift to the right. The reaction is trying to reestablish equilibrium by forcing it to the right to decrease the amount of that reactant that was just added. And so ultimately you'll end up with more of your product and less of that pink reactant. Now, if instead I took a reaction and, for example, I got rid of some of the product, so I got rid of some of that yellow, that change would cause a shift in equilibrium to the right again in order to try and make up for that loss. So if a substance is removed from a system, then the system reacts to produce more of that substance. It would cause a shift to the right. So let's use the party example really quickly to make sure we understand this. I have party A and I have party B. And let's say I'm at equilibrium. So there are individuals at party A, there are individuals at party B, but they're going back and forth from party to party at the same rate. Therefore, it seems like the total number of people at party A remains the same and the total number of people at party B stays the same. Now, what if suddenly a bunch of people showed up to party A? Well, if a bunch of people showed up to party A, there'd be way too many people at party A, and so some people would want to move over to party B. So there would be a shift to the right, so that some people would leave and go to party B and reestablish equilibrium. That's exactly what we did with the example in which the substance was added, in which that blue substance was added. Well, if you have two parties at equilibrium and you suddenly lose a bunch of people from party B, then the people at party A are going to say, well, our room's crowded, our party's crowded, let's go over to party B where they've got all the food because they just lost a bunch of people. So again, there would be a shift to the right, just like what we saw with the chemistry example. Now, let's say, for example, I get rid of some of my reactants. I can get rid of one of the reactants. Let's say I get rid of the blue, a little bit of the blue reactant, whatever that is. Well, that would be a decrease in concentration from party A, and so there would actually be a shift to the left to make up for that loss. Similarly, if I suddenly have an increase in product concentration, meaning a lot of people at party B, then there would be a shift of people to party A, meaning a shift to the left. So keeping in mind, if you increase the concentration on your reactant side, you're going to see a shift to the right. If you increase your concentration on your product side, you're going to see a shift to the left. If you decrease concentration on your reactant side, you're going to have a shift to the left. And if you decrease your concentration on your product side, you're going to have a shift to the right. So that's concentration. The next change that can occur is pressure. Now, at constant temperature, one way to change the pressure, you can either decrease the volume, which increases pressure, or you can increase the volume, which causes a decrease in pressure. So if I'm going to increase pressure, what happens is if I increase the pressure of the entire system, then the system is going to shift in the direction that has fewer moles of gas in order to reduce the number of moles of gas. So let's say, for example, I have 8 people at party A and I have 4 people at party B. If I increase the overall pressure by decreasing the size of all the parties, right? Meaning decreasing the area that they have to congregate. Then party A individuals are going to move over to party B because there are fewer people in that party, and therefore that will relieve some of the stress of that increased pressure. In contrast, if you have 8 people at party A and 4 people at party B, if I increase the volume and therefore decrease the pressure, some of those people at party B are going to say, well, you know what, there's plenty of room. We might as well go over to party A where there are more people. And so when you decrease pressure, then the shift will be towards the side that increases the number of moles of gas. So really quickly, if you see a system and you're told that the pressure increases, you know that the equilibrium is going to shift towards whichever side has fewer number of moles of gas. If you decrease pressure, then you're going to shift towards the side that has more numbers of moles of gas. The third and final change that you can make that can alter your equilibrium is changing the temperature. Now keep in mind, when we're talking about an endothermic reaction, your heat is going to be on your reactant side, while when you have an exothermic reaction, your heat is going to be on your product side. And so if you're going to increase your temperature, if you have an endothermic reaction, just treat it like it is changing the concentration. So if you increase the concentration on your reactant side, that would cause a shift to the right, and that is exactly what happens for an endothermic reaction. If you increase the temperature, it shifts to the right. If you decrease the heat, it would shift to the left. For an exothermic reaction, if you increase the heat, again, imagine you're increasing the amount of a product, you're going to see a shift to the left. While if you decrease the temperature, you're going to see a shift to the right. Now, there are 3 factors that do not cause a shift in equilibrium. The first is the addition of a catalyst. Now, a catalyst speeds up a reaction, but it does not cause a shift in the equilibrium. The next is the addition of an inert gas. An inert gas is not going to have any impact on the reaction. It's not going to react with any of your reactants or products, and therefore it's not going to have an effect on your equilibrium. And then finally, if you add a pure liquid or a pure solid, that will not have any impact on your equilibrium. So those are 3 things that will not change your equilibrium, cause a shift in your equilibrium. So let's look at an example. You guys are going to write this out, but I'm just going to talk it through. Okay? So for this example, it says that your delta H, your change in enthalpy, is less than 0, which means that this is an exothermic reaction, meaning heat is going to be on your product side because it's being released. So if we look, for A, it tells me that oxygen is added to the system. So if I increase the concentration of oxygen, that's going to cause a shift to the right. And so if I'm shifting my reaction to the right, that means my concentration of SO2 is going to decrease, but my concentration of SO3 is going to increase. So those would be your 2 answers. SO2's concentration decreases, SO3's concentration increases. Now, the reaction mixture is heated. If you increase the temperature of an exothermic reaction, because your heat is on your product side, you're going to see a shift to the left. And so as a result, your concentration of SO3 is going to decrease because you're shifting to the left, but your concentration of SO2 and O2 are going to increase. Now, if the volume of your reaction is doubled, what that means is that your pressure is going to decrease. So remember, if your pressure increases, you shift to the side with fewer numbers of moles of gas. If you decrease your pressure, you're going to shift towards the side with more numbers of moles of gas. So since I'm decreasing my pressure, I need to shift to the side that has more numbers of moles of gas. Well, that's towards my reactants because I have 3 moles of gas in my reactants and only 2 in my product. So I'm going to shift to the left, which means that my concentration of SO3 is going to decrease while my concentration of SO2 and O2 increases. Okay? For D, the addition of a catalyst does not change your equilibrium, and therefore it would have no impact because it decreases both your forward and reverse reactions, and therefore it has no overall impact on your equilibrium mixture. E, again, your increasing the total pressure, but you're increasing the total pressure by adding a noble gas. Remember, noble gas has no impact on the equilibrium mixture, and therefore that will have no effect either. And then finally, if you remove SO3, so you're decreasing your product, what that means is that you're going to have a shift to the right to make up for that loss. And so your concentration of SO2 and your concentration of O2 are going to decrease.